voice talks. So this talk is sort of a little bit of a sort of throwback to the time that I was sort of very active in sort of hydrodynamics. And in this sense, I want to apologize already at the beginning that I will not really sort of go into the details of what has happened in a sort of recent sort of month and maybe also last 2 years or so. Instead, I sort of chose to sort of try to give you a little bit of an overview, colloquium style, over how to set up hydrodynamics of equilibrium. And hopefully this will lead into a discussion of where we stand and how we go from there, basically. So the way that I set up the talk is that it is meant to sort of be an interactive talk. So I have, in principle, ample time to sort of enter some discussions. So please stop me, either by sort of just using your microphone, or maybe somebody can sort of also control what's going on the chat line, so that people can stop me if basically there's something there that I don't see while I'm giving my talk.
I'll have an eye on that.
Okay, so without further ado, let me sort of get started by sort of saying that if you open a canonical textbook on fluid dynamics, you'll find statements that say hydrodynamics requires a near equilibrium system in order to be applicable. That statement is in some sense synonymous with saying that you have to have thermalization or equilibration of the system for hydrodynamics to work as a quantitative description. In particular, in the context of heavy ion collisions, there has been lots of work in this context. We sort of recently sort of came to realize that in heavy ion collisions, the system doesn't really ever thermalize. That's not the story that I want to sort of go at. If you want to have a look at that, I put a preprint out there a couple of years back. I want to sort of really focus on hydrodynamics as a sort of off-equilibrium theory instead. So let us sort of try to question this statement that hydrodynamics requires near equilibrium conditions by sort of asking ourselves, well, is that really true? Can it be that maybe this idea of near equilibrium expansion is maybe sort of some sort of deceiving appearance, like a ship that's floating around, which has been sort of the standard way of expressing the way of fluid dynamics, but maybe is not really required for setting up the system in the first place. And the hint I want to use that maybe something with the standard textbooks is not quite right comes from these nuclear collision experiments that have been going on for a couple of decades now, mostly at the relativistic heavy ion collider RIC, but more recently at the LHC. To just give a little bit of history of that, the idea behind these so-called heavy ion collisions was that one wanted to learn about the so-called high temperature QCD phase, the quark-gluon plasma phase. Basically, as a sort of the motivation or some motivation for these colliders in the first place was to essentially measure the properties of semi-free quarks and gluons. And to sort of do so, people suggested that they needed some control experiments where the quark-gluon plasma was not there in order to sort of describe or distinguish between sort of this hot quark-gluon plasma phase and some ordinary QCD phase that didn't have semi-free quarks and gluons. And for that purpose, people suggested that one could look at light ion collisions, such as a proton on a lead nucleus, because people thought that, okay, there would be no QGP, the system would be too small, too short-lived. And the sort of ultimate control experiment, of course, was to be proton-proton collisions, where these are really, very small systems. They are smaller than 1 Fermi in size. They're extremely short-lived. I think that so far, there has been no suggestions that these systems really equilibrate. So the idea was that, okay, clearly hydrodynamics does not operate in proton-proton collision systems. So we have a very good control system that we can compare our sort of understanding to. I should also say that one of the main observables that people study is the so-called anisotropy. And the way this comes about is that if you think about the heavy ion collisions as two balls that basically sort of are colliding with each other, they typically will have a non-vanishing impact parameter so that they touch in a shape that's not really spherical. It sort of looks more like an almond-shaped region. And this region, which is sort of in this sketch given by this central ellipsoid here, after the collision will expand and will sort of show some dynamics. And in particular, it will evolve according to whatever dynamics the QCD sort of equations of motion tell it to do. To give you an idea of what the dynamics looks like, here's a sketch where we start with an almond-shaped region. We use fluid dynamics for the evolution, and we sort of look at how essentially the picture evolves as a function of time. So we can sort of do these simulations. And as you can maybe sort of see from this simulation, the initial almond-shaped region essentially evolves into a region that sort of is stretching basically in the other way. And what that means is that the velocity profile that is generated in these collisions must also be anisotropic. It is this anisotropy in momentum space that is directly measurable by experiments. So I have here a compilation of data from the Alice experiments, about 10 years old. And what you should sort of see is that there are a couple of data points, which are the symbols there, that measure not only the so-called elliptic flow, which is basically the cosine 2 phi component of these momentum coefficients, but also there's a cosine 3 phi component, the triangular flow, which in the data here is called V3. So these are routinely measured in experiments, and really sort of those are things that we can compare different descriptions of the dynamics to. So I want to sort of stay with these momentum anisotropies, and this here shows a slide that compares data from different experiments, ALICE, ATLAS, and CMS, in particular for heavy ion collisions on the very right-hand panel of this plot. The data points are these circles here. There are some error bars that you can maybe see. And the point to take away from this is that there are color-coded bands here which represent the results from using fluid dynamics as the main model to describe the dynamics of such a heavy ion collisions. Okay, so this is basically what you do with fluid dynamics. You sort of get these color-coded bands, and you sort of basically look at how these bands compare to the data, and you find that, okay, there is at least some region where the bands coincide with the experimental data. For higher momentum, the discrepancy gets larger, but there is at least an overall reasonable agreement. Now, the punchline from this three-panel plot is that you can use exactly the same hydrodynamic model with exactly the same initial condition, the same condition that produces these comparison to experimental data, which measures hadrons, and use it for other collision systems. The middle panel here is a panel where we have run the model for light heavy ion collision, so proton on lead collision. And the very left-hand side is the one where we run the model for proton-proton collisions. And what you should take away is that there are essentially no free parameters once we have fixed the model parameters so that the lead-lead data is described by the model. So there are no free parameters. It basically sort of is completely fixed. And if you look at the comparison between the fluid dynamic model with the experimental data for proton lead and proton-proton collisions, you see that while there is still some discrepancy, the model overall works amazingly well, given that it has essentially no free parameters. So we sort of call this one fluid to rule them all, to just describe the, if you want to, surprise that a single fluid dynamic model with no free parameter out of the box would give you a pretty impressive quantitative description of, in particular, the particle spectra that come out from proton-proton collisions. Now, one conclusion that I think one can draw from this is that apparently fluid dynamics works quite well away from equilibrium. We don't think that proton-proton collisions lead to an equilibrated system, yet we sort of see that fluid dynamics as a model does extremely well in describing the data that comes out of proton-proton collisions. The obvious follow-up question of that statement is, why does it work so well? Why is it that fluid dynamics is unreasonably successful in describing systems that are not equilibrated in any sense of the word? The main thrust of my talk is that there has been quite a bit of progress in understanding that question in the last 10 years. And I'll be sort of trying to focus on the basics in this talk rather than the very recent developments. There's lots of exciting stuff happening, which I won't cover in my talk. I apologize for that. I will sort of try to give you the main idea behind this and hopefully sort of provide you with the opportunity to really sort of read on to the more recent literature and see what's going on there if you're interested in joining in the discussion. Essentially, what I'll be talking about has been the sort of substance of the textbook that my wife and me have sort of written about the topic. So if this is something that is available as a textbook from Cambridge University Press or by preprint at these at the archive number that's listed here. To get started, I wanted to talk about, if you want to the cookie cutter type of fluid dynamics, I want to get started by talking about fluid dynamics near equilibrium. There are many derivations of the equations of motion for fluid dynamics. In the following, I will be focusing on what perhaps is the most general approach, which is effective field theory. And in this approach, one finds fluid dynamics as the effective field theory of long-lived, long wavelength excitations of whatever system you want to consider. In the EFT language, one has to figure out what are the good EFT variables to build the effective field theory on. And for fluid dynamics, that's very easy to come by. If you think about typical examples of fluids, you fairly quickly will find that you need things like a pressure, maybe a density or energy density, and a fluid velocity. In a AFT setup, what one then does is one writes down quantities using the EFT variables and then does a gradient expansion of those variables. For fluid dynamics, the central object that one wants to do this algorithmic sort of derivation is the so-called energy momentum tensor. So if you want to sort of study, or if you want to sort of write down what a rank 2 symmetric tensor is that obeys certain symmetries, such as Lorentz symmetry, then you find that if you have the fluid 4 velocity as a building block, as well as the energy density as a building block, which is a Lorentz scalar, and the metric tensor to lowest order gradients, meaning no gradients, you find that essentially this is the only form that you can write down. And then you can improve upon this leading order EFT energy momentum tensor by allowing first order gradients. And you find that there are structures such as these first order gradients on the fluid velocity that appear. And of course, there are other structures as you go on and include higher order gradients in the setup. The main point here is that the structure of the energy momentum tensor, meaning this form of this expansion in gradients, is universal. The structure is fixed. The only thing that really cares about the specific fluid that you're trying to describe is the value or the relation between these coefficients. How, for instance, the pressure relates to the energy density, how things like the shear viscosity relate to the pressure, and so on and so forth. In particular, in this approach, there is no notion of thermal equilibrium. However, what there is that since it's an expansion in an EFT, there's sort of, if you want to, assumed idea is that the gradients that we sort of expand around are small. Now let's try to sort of take this idea, but try to push it out of this near equilibrium regime to where, if you want, so the gradients are larger and the sort of setup becomes rougher. What if we had large gradients? The example that I like to take for a large gradient example is if we had a certain function, let's take the function to be the exponential function, and we want to get an approximation of this function for values of x that are not small. Let's say they are x of order 1. What we are doing is a gradient expansion. So we would write down powers of x for the approximation of our function f of x. Let's say if we go to 4th power in gradients, we would write down 1 plus x squared over 2, and so on and so forth, plus x4 over 4 factorial. And then if we plug in the value of x that we are interested in for our approximation, we would find that f of 1 happens to be something like 2.08, which is reasonably close to the actual value of the function here. Of course, for this particular example, this gradient expansion works for any value of x, provided that we have sort of taken enough gradients in the approximation, because the function we are expanding, this exponential function, actually leads to a convergent series for all values of x. Nevertheless, we could ask if that is maybe what's going on in fluid dynamics. So clearly, we can sort of try to use the same idea. We can try to include higher order gradients in our effective field theory gradient series. This has been pushed to a surprisingly high number of gradients. So for instance, for Bjorken flow, there are now routine examples where you can go to a large number of gradients, something like 240 of them. Unfortunately, what you find in pretty much all of the examples that sort of are given in this context is that the coefficients in this gradient expansion, which are now denoted here as alpha n in this expansion here, typically go like n factorial, which is a clear sign that the gradient expansion is not a convergent series, but it is rather a divergent series. This is the bad news. The good news is that this divergent series seems to be Borel summable in a generalized sense. For the example that I showed on the previous slide, this was the example where you have a high degree of symmetry. You basically sort of impose a Bjorken flow on a background that is homogeneous in transverse space, and you use a holographic plasma to sort of get the number or the value of these transport coefficients. And for this particular case, the Borel resummation has been sort of carried through. And what you find is that for a specific function, such as, for instance, the temperature, T, as a function of the Bjorken time tau, you find that the result of the Borel resummation has two pieces. There's one piece which I call T hydro, which I'll talk about in a moment. And there's an additional piece here, which is the exponent of an integral of t to the minus 1/3. This is a little hard to interpret, but for later, I will sort of talk about this hydrodynamic attractor, but for now, I want to sort of concentrate on these extra pieces here. And I want you to sort of realize that what we have here is something that is comparable to having a function f of x, that in addition to having a regular part, like the exponential function itself, has a part that is actually non-analytic in the expansion around x is 0, something like e to the minus 1 over x. This is what you basically have when you look at the actual Borel resummation of the gradient series for the example of ADS-CFT. So this, in my nomenclature, I call the part that is sort of, if you want to analytic in the gradient expansion, I'll call that the hydro part. and the rest I call the non-hydro part. The non-hydro part basically has this form here. It's the exponential of basically an integral of tau to the minus 1/3. And the number that's sitting in front of this function here has been measured numerically with reasonably good precision. So you have some 4 digits behind the comma in this work by Michael and company. And that's really sort of the number that comes out by sort of doing this program of performing the Borel resummation of the gradient series itself. Now this number, 3.11 minus 2.75i, is not any number. This number actually happens to be the same as the lowest lying non-hydrodynamic quasi-normal mode of a black brane in the corresponding ADS5 geometry that was calculated about 10 years earlier by Andrei Starinets. As a reminder, what you do in ADS-CFT is you start out with a black brane and you consider small fluctuations of that black brane around equilibrium, and you look at the response of the black brane with respect to these fluctuations. And what you get out of this is the so-called quasi-normal mode spectrum of the brane. This spectrum has different channels depending on which kind of perturbation you set up. The nomenclature is non-standard, but there is more or less a consistent nomenclature in the sense that there's a sound channel. And this sound channel is the one that I have here as an example. Whoops, I'm sorry. That I have here as an example for this plot here. These are the quasi-normal mode frequencies for the sound channel of the black hole. There are 2 which are denoted by slightly thicker dots here. These are actually corresponding to the actual sound modes of the black brane. And the rest of them, which are forming this so-called Christmas tree structure, these are the non-hydrodynamic quasi-normal modes. And it is these non-hydrodynamic quasi-normal modes that you see emerging from Borel resumming the standard hydrodynamic gradient series in ADS-CFT. I want to sort of emphasize.
May I ask a question?
Yes.
Can you go back a couple slides on the slide where you're showing the T of tau that's made up of the hydro piece and the Borel piece?
Yes.
So here, the way people determine the Borel frequency is they compute the actual T of tau, then they evaluate T hydro of tau using the hydrodynamic constitutive relation?
No. No,
yeah,
the way
okay,
that
good.
the way that this is done is that, let me go back one more slide. The way this is done is that you calculate the gradient series by sort of doing the same process that would lead to a determination of, for instance, the viscosity coefficient in ADS-CFT, so the 1/4 pi. But there are generalized versions of viscosity that come as higher order gradients. And you do that not to 2nd or 3rd order, you do that to order 240.
Yes.
So you have all these numbers, and that defines a gradient series. This series is divergent, but you can use the series to define a Borel transform. Once you have the Borel transform, you need to sort of basically go and calculate the back transform, the original function that you started with. To do that, you have to close a contour, and closing the contour basically leads to 2 pieces. There's one piece which I call the hydrodynamic piece, which is this piece, which is some function that sort of comes out from essentially completing this program. And there are other pieces which come from you having to sort of go around some poles in the complex plane in the Borel plane, essentially. And this is what gives you this complex frequency omega Borel. I'm realizing that it's hard to follow the actual process if you don't have an actual equation to go through. This is not an easy process to do. Here, I really sort of just want to emphasize that this is a possible thing that people have done in practice. And you basically find that there are these 2 pieces. Does that answer your question some way?
Yeah, in some way. I guess I was trying to understand to what extent you need to tweak omega Borel by hand, or whether it just emerges from resumming the
It,
series.
yes, it really just emerges. Essentially, omega Borel is set by the singularity that's closest to the origin of the Borel plane. It's fairly hard to tweak this frequency. For the other frequencies that also appear here, which are then sort of higher order, if you want so, this would correspond to the higher order quasi-normal mode. My understanding is slightly trickier numerically to extract those. But as far as I understand, the first 4 or 5 non-hydrodynamic quasi-normal modes have been successfully extracted using this process with reasonably good numerical accuracy.
Okay.
So there's essentially no tweaking involved.
Okay, thank you.
Okay, right. So essentially what I was trying to say next is that this is an example where we have a concrete realization of this resurgence process for a strongly coupled field theory that can be set up and probed by ADS-CFT. However, the physics of these non-hydrodynamic modes, these non-hydrodynamic quasi-normal modes in the case of ADS-CFT, is not unique to strong coupling. And the example I want to give you is that if you essentially look at the pole structure of the two-point function for weakly coupled theories that are realized in terms of kinetic theory, you have essentially the same picture. You have two hydrodynamic poles that correspond to the sound poles. You don't have quasi-normal modes, but what you have is you have a logarithmic cut. Okay, and what this animation, I'm sorry, I'm going back and forth here. What this animation is showing you here is what happens to the structure if you change the wave number at which you probe the theory. The specific thing about kinetic theory is that if you go above a certain critical wave number, the hydrodynamic poles become subdominant with respect to the logarithmic cut. And depending on your choice of the logarithmic cut, they either completely vanish from the principal Riemann sheet, or they are just sort of lower down in the complex plane if you choose your logarithmic cut to sort of go in a different direction. So this, if you want, so this competition between hydrodynamic poles and all the rest, the non-hydrodynamic fingerprint of your theory that you're considering, that seems to be a sort of pretty common feature that extends away from strongly coupled theories that's also present in weakly coupled theories in particular. So I would basically try to formulate what I've just shown you in pictures as a sort of finding. The finding that I want to sort of get across is that the reason why this hydrodynamic gradient series is divergent in the first place is because there are non-hydrodynamic modes, and these non-hydrodynamic modes lead to essentially essential singularities in the expansion around zero gradients. These are the reason why your hydrodynamic gradient series is divergent in the first place.
Can I ask a question?
Yes.
So this ignores hydrodynamic fluctuations, which probably also make the gradient series non-convergent. Did you have any comment on this?
Yes. So yes, this, you're absolutely right that all I'm telling you in the main part of my talk is limited to classical fluid dynamics, meaning absence of fluctuations or long time tails. If you want, so think of it as a large N limit of whatever theory you're considering. It is true that hydrodynamic fluctuations will generate additional non-analyticities in your setup. Depending on the dimensions that you're probing, these will even set up problems earlier than the ones that I'm discussing here. However, I have some mild hope that carrying through this whole progress of setting up the hydrodynamic gradient series, at least formally, for something like a hydrodynamic action, could lead to a resurgence analysis that includes fluctuations. But I want to basically say that this is something that has not been done. And for the moment, think of what I'm telling you simply as the large end limit of whatever theory you consider.
I see. Thank you.
But these non-analyticities, they will be branch cuts, right? Not additional poles.
Most of the time, these are indeed branch cuts. They come in as fractional powers of the frequency, for instance. I don't want to say that it's impossible for them to sort of do something else, but the ones that I know of typically are branch cuts. That's correct.
I mean, in theory, you might worry that, because the radius of convergence is 0, that any fancy analyticity tricks might have some issues. But of course, I agree that within the large N expansion, everything is well controlled.
Yes, that's right. I mean, I should probably have stressed that as far as I know, nobody has actually tried successfully to carry out a program of resurgence on the level of a hydrodynamic action. But at the moment, I don't see why it would be impossible to at least get this process started. I think that's all I can say at the moment. So since this is a colloquium, I'm told, I want to sort of briefly say a little bit about these non-hydrodynamic modes. Non-hydrodynamic modes, the ones that are maybe sort of most known in the physics community outside of these fluid dynamics specialists, are the ones that appear in the ring down of a black hole following a black hole merger. So I have my little simulations of black holes here on the upper right hand part. And essentially what this is supposed to be showing is that once basically, so you have your inspire of your black holes, you see a gravitational waves data that has been, for instance, observed by LIGO. You see a merger in which the spectrum is complicated. And after the merger, you have single black hole that is sort of going to equilibrium by ringing down. It is this ring down spectrum that carries information about these non-hydrodynamic quasi-normal modes. And indeed, it is this spectrum that LIGO has directly used to extract things like the quasi-normal mode spectrum of an actual astrophysical black hole. So we know that these are physically there. We have observed them using gravitational wave data. And it's those modes that I'm talking about, just generalized not to actual astrophysics black holes, but sort of strongly coupled ADS-CFT black holes. With this aside, I wanted to come back to my main story, which is the discussion of alpha equilibrium hydrodynamics. I have linked the non-hydrodynamic part of the Borel resummed fluid dynamic quantities to these exponentially falling non-hydrodynamic modes. Okay, these quasi-normal modes have the property that they are typically highly damped, they're over-damped, and as such, the amplitude dies out as you sort of follow the system in real time. I've also said that there's a second piece, which I called the T-hydro in the example I was talking about earlier. And it is this piece which I'll call the attractor. I'll call it the attractor because that was essentially the name that Michael Heller and Michael Spalinski chose in their seminal paper, where they studied a certain set of equations that exhibited essentially these two properties. What they did was that they started out a system that is controlled by some initial condition, and that system goes to fluid dynamics in the very late time limit. Okay, so it has the property that if the system is indeed thermalized, the system will behave according to the equations of relativistic Navier and Stokes. And what they found is that if they chose different initial conditions, which are these different lines here, then the evolution of the system expressed in the correspondingly scaled quantities had this following form. So they would start with one particular initial condition, it would follow a form and then follow essentially a certain line. And if they started with a different initial condition, you would start with different line here, but you would essentially be attracted to the same line that is called the hydrodynamic attractor in this plot here. So what is the upshot of this is that this line, which is sort of here magenta, this piece here is indeed nothing else but the attractor piece of the Borel resummation of the gradient series. It is this piece here that all the other sort of initial conditions converge on as time goes on. And in that sense, it provides essentially a generalization of the notion of fluid dynamics to of equilibrium pieces. The study of these hydrodynamic attractors has not been limited to this particular model that was studied here. This is some RBRSS model, which I sort of show here. One can look at different systems to see if the behavior is similar as you express the behavior in terms of these scaled functions f and w. The example that I'm showing here is from a different work where I want to draw your attention to the right-hand panel, which is labeled ADS-CFT, and the central panel, which is called Boltzmann. Let me get started with the Boltzmann picture here. What's done here is that you start out with kinetic theory in the relaxation time approximation. You give the system, it's kinetic theory in Boltzmann in relaxation time approximation and some additional degree of symmetry. This is also Bjorken flow, so homogeneous transverse space and just longitudinal expansion according to Bjorken scaling. And you start the system with different initial conditions and you follow these gray dots here that are sort of labeled. These are not labeled here. And what you find is that the behavior is qualitatively similar to the one that was found by Heller and Spalinski. You find that there is a certain curve, which is labeled here in black, that all of these initial conditions tend to after a very short time. And this black curve here also happens to be the curve that goes on to, for instance, the Navier-Stokes equation, which in this plot, on all of these three plots, is labeled by this blue dashed line shown here. So it is this attractor line that you can find in kinetic theory, in a weakly coupled sort of dynamical theory that goes on to hydrodynamics at late times, but exists also for much earlier times where gradients are stronger. For the ADS-CFT case, it's again qualitatively similar. You start with different initial conditions, which are again these black dots here. The main difference is that here, the approach to this universal hydrodynamic attractor curve is non-monotonic. For instance, if we look at this curve here, we start below, it overshoots again, and then eventually settles down onto the attractor. The reason for that is that the approach to the attractor in ADS-CFT has a complex frequency, which has a real and an imaginary part, and as such as it contains a piece that is exponentially damped and a piece that's just oscillating as a cosine. So that's why it's overshooting and sort of oscillating around the attractor, whereas in kinetic theory, in the simplest case here, the frequency is purely imaginary, and as such, the approach to the attractor is simply an exponential decay. There's no overshoot here. So what this example is meant to highlight is that you can look at different microscopic theories of a certain plasma out of equilibrium, such as a strongly coupled plasma via ADS-CFT, or a weakly coupled plasma that's described by kinetic theory, and you find the same universal feature. There are initial conditions which are attracted to a unique line, which is basically becoming fluid dynamics once the gradients are small, but exists in its own right, even in a regime where things like the gradient expansion would not be expected to work. The finding that I want to emphasize, which is also my take-home message, is that these hydrodynamic attractors offer a quantitatively reliable out of equilibrium description of the system dynamics as long as the contribution from these non-hydrodynamic modes is small enough that it can be neglected. And this finding implies that there is a notion of fluid dynamics that does not need thermal equilibrium, that does not need isotropy. It basically is just a property of the competition between the excitations of hydrodynamics, these hydrodynamic poles, if you want so, and all the other modes in your system. If the hydrodynamic modes are longer lived than the rest of them, then hydrodynamics exists as an out of equilibrium description. If, however, the other modes are the dominant modes which are living longer than the hydrodynamic modes, then the system basically does not offer hydrodynamic description, and hydrodynamics has effectively broken down. However, this competition is such that the competition between these modes really sort of happen at a completely different scale in terms of gradients when you compare it to the notion of isotropy or thermal equilibrium that is traditionally thought to be the relevant criterion for the existence of hydrodynamics. I want to sort of, let me sort of see, how much more time do I have? I don't want to sort of use all my time.
You've got at least 15 minutes, I would say. Yeah, 15 minutes is normal, yeah. You got some questions.
That should be easy enough. So there are a few more things that I wanted to mention, and then hopefully there will be more questions at the end. So one of them I wanted to mention is that in the examples that I've shown so far, these were attractors that had an extremely high degree of symmetry. In particular, the motion was essentially confined to just one direction. This was Bjorken flow. So one would basically ask, well, I mean, maybe these are artifacts from the high degree of symmetry that you've set out to do. Maybe these attractors don't really exist when you start breaking some of the symmetries. And that could have been the case. However, I wanted to point to the picture that I'm showing here, which studies a system that is actually evolving in 2 dimensions, and it has a 3rd dimension, which is expanding longitudinally. And this system basically sort of has no symmetries in the transverse plane. It can sort of be arbitrarily complicated flows. Yet, if you follow different initial conditions and you sort of, again, express it in these proper scaling variables that you can sort of define, then you find the picture that's shown here. You have different initial conditions, which are these black lines. They start out here, they sort of turn around, and then at some later times, they basically sort of follow essentially a single sort of line here that has all the properties that we would usually associate with a hydrodynamic attractor. So it seems like, at least in these examples that don't have as much symmetry, hydrodynamic attractors are still present. There hasn't been an exhaustive search for these attractors in systems that have essentially no symmetries, but I think the fact that in all the cases that we have looked, we found them, sort of seems to suggest that, okay, maybe this concept does apply even in systems where that are more realistic, that have less of these sort of special symmetries that were used in order to find these semi-analytic attractors in the first place.
A question? So here you're talking about the symmetry of the flow. How much of this, what about the symmetry of the underlying theory? How much of this relies on, Lorentz invariance? Do you think this attractor technology could be extended to theories without Lorentz invariance and maybe even without translation symmetry for condensed matter physics applications?
Yes, good question. So basically, all of the examples that I've shown here use Lorentz symmetry as a sort of a symmetry. The main reason for that was that the applications that I and other people had in mind were for relativistic fluids that are sort of constructed using Lorentz symmetry. However, I don't see any reason why these attractors would go away if you stop using Lorentz symmetry. And one of the reasons simply is that the equations of motions that these are based on can be expanded for small fluid speeds, such that you basically sort of forget about Lorentz invariance, and the attractor basically would still be there. So that's why I think that most likely, if you don't impose Lorentz invariance from the start, you basically consider ordinary fluids. If you want non-relativistic fluids, I would be very surprised if you don't find attractors there. Are there also attractors if you consider momentum relaxing sort of systems? I don't know, but I find it plausible to think that they are. The reason again is that essentially all you need is a system that has some sort of traditional hydrodynamic degree of freedom associated with it. And if that's the case, then in all of the cases that I know of, this existence of a hydrodynamic mode generalizes then to some sort of attractor as you push it farther away from equilibrium. That's my hunch, if you will. But I don't really know about actual sort of studies that have proven that in any sort of example that you are probably thinking of, like condensed matter systems or something like this. I think it's worthwhile looking for them.
I see. Interesting. Thank you.
Okay. Yes. So fine. Okay. So let's say that these attractors are there. We only really have characterized or started to characterize attractors for a handful of cases or theories. It's much easier to just use standard hydrodynamic solutions for the case that you're interested in. So what's wrong with that? Or can we maybe use some of the technology that we've discussed to discuss when exactly standard hydrodynamics applies if it's not near equilibrium? The hint that I want to take is a hint from QCD thermodynamics, which at first glance seems completely unrelated to the problem that I have. In QCD thermodynamics, one thing you can do is you can try to solve QCD at finite temperature using a perturbative series. You find that the series is divergent. It's a series in G. It's a divergent series. And as such, it doesn't seem to be making a lot of sense. However, we know that the actual answer for thermodynamics of QCD is a well-defined non-analytic function. It's perfectly fine to plot things like the energy density as a function of the temperature for QCD. So using the divergent series, in particular to a high order, to try to describe this function is just not the most efficient way to getting there. However, what you can do is you can try to do different things. You can do resummations, for instance, or you can just try a very low order approximation of your perturbative series. Just take the leading order coefficient G square and compare it to the lattice QCD data. And you find that surprisingly, you do a pretty good job. Okay, so the line that I want to have you look at, even though that's not really what these calculations are, is these dashed lines here, or sorry, the solid line here, and the lattice QCD result is shown in this gray band. And what you find is that a low order truncation of the divergent series gives you at least a reasonable quantitative agreement with the non-analytic function. So what if the same thing was true for hydrodynamics? What if a low order hydrodynamic result happens to coincide with the non-analytic attractor solution at moderately large values of the gradients? If that's the case, then this would offer a suggestive explanation about why Navier-Stokes, which is a low order truncation of the hydrodynamic gradient series, quantitatively works well for out of equilibrium conditions. Of course, we could actually check whether this is actually true. So let me just go back and show you the corresponding plot for the cases where we can look at these low order truncation. Let's, for instance, focus on the Boltzmann case here. As a reminder, the black line here is the hydrodynamic attractor, and the blue dashed line, that's Navier-Stokes, okay? And what you find is that Navier-Stokes, as such, does a reasonably good quantitative job of describing the attractor down to gradient strength expressed at this as this dimensionless quantity here of order unity. Okay, so this does not say the gradient has to be exponentially small for fluid dynamics to work, low order fluid dynamics to work, but it has to be only about order 1. You look for a different system like ADS-CFT, and you essentially find the same thing. Low order hydrodynamics coincides with the attractor at gradient strengths that are order unity. So that's basically what I mean when I say this is really a finding of studying these attractors compared to low order truncation of the hydrodynamic series. So in the last few minutes, I want to sort of try to go away from what has been the central message of my talk, that hydrodynamic models apply for moderately out of equilibrium situations. It's off equilibrium, it's order 1 gradients, but it's only moderately out of equilibrium. In the last few minutes, what I want to do is I want to sort of see how far we can push the envelope and talk really about fluid dynamics far from equilibrium. To look at that, I want to highlight the cases that I've shown here. And I want to say that the point that I'm trying to make is that these attractor solutions actually extend all the way to gradient strength of infinity in these simple cases that we've studied here. So as such, some notion of fluid dynamics, namely the notion that ties it to the existence of an attractor, would extend clearly far from equilibrium for these systems. One way of trying to get at this would be to say that, okay, we have this hydrodynamic gradient series that has 0th order, 1st order, and higher order terms. But we could try to, if you want to, resum all these higher order terms by just putting them in the value of the coefficients, the pressure, the energy density, the shear viscosity, where these generalized Borel resummed coefficients then depend on the gradient strength at which you evaluate them. This is not a new idea. So this is basically something that has been advocated as all orders hydro already a number of years ago by, for instance, Ed Churiak and Michal Lublinsky. And it certainly isn't an exact sort of statement in the sense that we know there are some terms that you can't just put into these structures that you already have at low orders. But I think there's some chance that using this concept of an effective gradient strength dependent viscosity for really out of equilibrium systems could make a lot of sense. I will not go into the details here. Rather than I want to sort of just say that, okay, there's a notion that far from equilibrium hydro exists if you have robust attractor solutions. If you go that direction, you find that the effective viscosity that you sort of have in your systems will typically be smaller than your equilibrium viscosity. And this could potentially sort of also hint for other sort of descriptions of problems, for instance, at strong coupling, because it is not only these hydrodynamic coefficients that you get out, it's a whole structure. So for instance, in ADS-CFT, there could be a metric that is an attractor metric for the system that you're studying. So it is larger than just, or potentially larger than just the hydrodynamic gradients that you're resumming. With that, I'm probably out of time, so I quickly want to summarize by sort of giving you my conclusions. I advocated that standard equilibrium requirement for hydrodynamics may just be too restrictive in practice. There is a considerable numerical as well as experimental evidence for instance, nuclear collisions that fluid dynamics does apply in out of equilibrium situations. In a nutshell, the theory development in the past 10 years has been that the hydrodynamic gradient series generally diverges, can be resummed, and gives rise to non-analytic attractor solutions. If you have these attractors, they may be thought of as a generalization of hydrodynamics to off equilibrium. And it so happens that, at least in examples where we have control over these attractors, we find that the attractors are well described by a low order truncation of the divergent gradient series, hydrodynamic series. If one wanted to sort of push this to far from equilibrium situation, one can try to characterize the off equilibrium hydro by an equilibrium equation of state and non-equilibrium transport coefficients. Clearly, there's a lot of work that still needs to be done to really sort of make this into a sort of new paradigm for fluid dynamics. As a sort of random list of future directions, I want to sort of ask whether there is a hydrodynamic attractor, if it exists, for QCD. We have already sort of discussed a little bit during the talk the possibility of looking for attractors that include the physics of fluctuations or long time tails. And something that I didn't discuss is that clearly these attractors are intertwined with this presence of non-hydrodynamic modes. These are very poorly studied in actual systems that we sort of can test in nature. So maybe it would be a good idea to learn more about non-hydrodynamic modes in actual sort of physical systems. And there are a number of other things that I sort of can think of that would be a good way to sort of go in the future. And if you are interested, you can look at this chapter in this hydrodynamic textbook that I advertised earlier. With that, I want to thank you for your attention, and I'm hoping that there are some more discussions or questions in the few minutes that we still have.
Yeah, thank you very much. I will hand over the discussion as I promised to Paul already. I'll hand it over to Martin. Martin, if you're there.
Yes, I'm here.
Okay.
So yeah, thanks for this nice talk. So are there questions? Yes, so there's one, Christian Ecker, please.
I actually have a question. So it's not directly related to what you have discussed in the talk, but it's about the formulation of hydrodynamics for quantum field theories on curved spacetimes. So these, for these, the notion of energy density and pressure, they can be ambiguous because of anomalies. And it seems like these variables then in the hydro expansion are not the most natural ones. So what I want to say is it seems like the hydrodynamic expansion in these variables seems to be scheme dependent in for theories on curved spacetimes. Can you comment on this?
Yes. So let me sort of see if I understand you correctly. So you're worried particularly about the Weil anomaly?
Yes, exactly. Things like that.
Okay. Yes. Yes, the Weil anomaly is something that comes into play whenever you want to formulate fluid dynamics in space-time dimensions that are in particular even. So in 4 space-time dimensions, you basically would have a term that's something like Riemann squared. Riemann squared basically means that you have this term basically contributes at 4th order in gradients. So basically it would show up in the expansion of the energy momentum tensor as a 4th order gradient term. I think that in principle, it would have to be taken into account. It's just that for these low order fluid dynamics equations of motion, it typically has not been taken into account. But you're right that if one would sort of think about fluid dynamics okay, maybe sort of backing up. So these lower orders here for the energy momentum tensor, these terms here are formulated in principal curved spacetime. The G mu can be any metric, and in particular, it is this formulation that you use to calculate, for instance, the response of a neutron star, because you put in GAB to be the Tolman-Oppenheimer-Volkoff metric. So that's basically already what you use. All I'm saying is that this can be extended to higher orders. And you're right that at fourth order, you have to take into account the Weil anomaly. As far as I can tell, it's not a problem for the expansion itself. All that the Weil anomaly does is say that even if you thought you would start with a theory that is conformal, the Weil anomaly would destroy that notion in 4 dimensions, because it tells you that, okay, your theory has a conformal anomaly. So what that would mean is that you would have to add this particular coefficient that destroys the symmetry that you thought at the classical level. But I think there's no principal problem in including it as a coefficient in your expansion. You would just sort of break conformal symmetry and have a non-conformal energy momentum tensor. I don't see any principal problem there.
Yeah, so maybe I confuse things here, but I thought if you have a field theory on curved spacetime, your notion of the stress tensor itself is ambiguous. So it depends on, in the definition of the quantum stress tensor, you arrive at the ambiguity in the definition of the energy density and the pressure itself, I think, where you have to fix some observables in order to fix these ambiguities. What I want to say, this is typically epsilon and p that appears in the expansion. They are not scheme independent in general.
Right. I mean, you do have you do have this issue already essentially at the level of the first order gradient term. Okay, so this is not something that is related to the Weil anomaly as far as I can tell. This is really an issue about what do you mean by energy density for a quantum field theory? And indeed, that is a sort of discussion that I completely skipped in my talk here. There are different ways to deal with this. The way that I dealt with this in the setup, even though I didn't talk about this, was to say that I want to define the energy momentum tensor, or I want to define the energy density as being the eigenvalue of the time-like eigenvector of the energy momentum tensor. That is a choice that I made. The choice makes sense as long as my field theory has, or the dynamics of my field theory has, a local rest frame. It does not make sense if the system does not have a local rest frame. And this choice sort of, I think, is reasonable even on curved spacetimes, as long as your dynamics, your quantum field dynamics, is not too extreme. Whether it is the most reasonable definition of an energy momentum tensor or energy density, I don't know. I think it's a workable definition. But okay, so I think what I say is that there are some deep issues here that one needs to sort of think about. I think that if one defines the energy density as the coefficient or the eigenvalue of the time-like eigenvector of the energy momentum tensor, that solves a lot of practical problems. It may not be the most general sort of definition, in particular if a local rest frame doesn't exist. That's what I would say. I'm not sure if that really answers your question.
To some extent, yeah.
So there's one further question by Blaise. So please go ahead.
I don't think I was asking a question. I was just clapping. I'll stop.
So you were raising the hand. Okay. So are there further questions? So
I do have a question.
Okay.
When you were showing those plots of the tractor, that you had like this kind of like oscillation before reaching the tractor for the time evolution in the ADS case, and in the Boltzmann case you didn't. So you mentioned that you had like this relaxation time approximation. Would you expect, I mean, if you include in the the Boltzmann equation something like a more realistic type of collision integral, would you expect something like this type of oscillations?
That is a good question. So yes, people have thought about trying to put in different forms of the collision kernel. I think it's quite possible that you get oscillations in this case. I'm trying to remember if I've actually seen complex frequencies emerge for these collision kernels that have been studied. At the moment, I can't really think of a case there, but I would say I think it's possible, but if somebody has studied this, I apologize. I can't really recall their paper at the moment. So I think it's possible, but I can't remember if the specific set of paper there.
Because what I've seen, at least in non-relativistic cases, is that even if you consider a kind of like more realistic collision integral, what you get is just like a branch cut in the, if you study like the pole structure of the.
Oh, these do have branch cuts. Okay. So let me sort of try to go back to the picture that I showed here. Let me see if I stop this. So this essentially is the structure of the retarded two-point correlation function in kinetic theory with a relaxation time approximation. You have these two hydrodynamic poles and a branch cut. So
Exactly.
that's certainly
yeah, exactly that's what I meant. That even if you go beyond the relaxation time approximation, you don't see anything like these isolated quasi-normal modes you have in holography.
Right. I as far as I can tell, nobody has seen isolated quasi-normal modes in a weakly coupled theory. This is a statement that I can make because there are examples where you can solve the quantum field theory directly using a large n limit, and this doesn't require ADS-CFT or anything like that. It's just large n. You can solve the path integral and you find branch cuts. But that doesn't mean that if you have a sufficiently complicated collision kernel that you couldn't have both, like a branch cut plus additional poles. At the end of the day, my suspicion is that a little bit, it then depends on how you structure your collision kernel, right? I mean, these are pretty complicated objects. So if you make something up, you could potentially conjure it such that you do get poles in addition to your branch cut. I think I would have a hard time seeing how you could end up with just poles in the weakly coupled field theory, simply because you're expanding around the non-interacting theory, and that non-interacting theory has this branch cut, and it's extremely hard to get rid of it.
Okay, so but then that's the origin of not seeing the oscillations, right? The absence of those like isolated poles.
Right. Yes. I at least I can't remember having seen any oscillations. Yes. So clearly in this structure here, there will not be any oscillations. This just gives rise to basically the damp. Okay. So maybe sort of to demystify what's going on here. So if you do Bjorken flow on these systems, you're essentially sitting at K0, in which case the branch cut here is a single pole. So it looks like it's exponentially damped without any oscillations, but that's just an artifact of Bjorken. It's not an artifact of the branch cut. Does that maybe sort of shed some light on the discussion?
Okay, thank you. Yeah. Yes.
So are there further questions? So if that's not the case, then again, thank you much for your nice talk. And yeah, so the next HoloTube meeting is then next week, again at 4 p.m. Central European summertime. Okay, thank you.
Thank you.
Paul, can you also stop recording? You are the last remaining host. So